Good morning, nice to meet you all. This is Inigo López García from the University of Deusto, and in the following minutes I'll be presenting the LOGISTAR project on behalf of all the authors. So particularly, I'll be describing the routing optimization engine used in this project to optimize the planning. So let me share the slides with all of you. Okay, there we are. So here we can see the contact information for myself. Okay, so let's begin describing the project. So LOGISTAR project is an Horizon 2020 European project which aims for an effective planning and optimization of transport operations. And to tackle this objective, among others, it takes advantage of horizontal collaboration and backhauling and intermodal transshipment. So the final aim of LOGISTAR is to deliver a decision-making support tool for planning and optimization. The motivation to develop this project is twofold. On the one hand, we have the necessity of developing such an efficient decision support system, and on the other hand, we have the optimization, the complexity of the problems to optimize. So overall, we can say that LOGISTAR considers three scenarios. The first one is the consolidation of shared centers. The second one is the conjoint routing, the collaborative optimization, and we also have the backhauling. So we can say that LOGISTAR focuses on optimizing multi-point vehicle routing problems, taking into account distinct restrictions or characteristics, such as capacity of vehicles, the spatial restrictions for goods, co-loading, pickup and delivery locations, or multi-depot locations for backhauling and time-dependent windows. Okay, so to optimize this vehicle routing problem, this complex vehicle routing problem, we use a meta-heuristic based on large neighborhood search. This meta-heuristic is based on destroy and repair operators, which are used to explore the state space of possible solutions, such as what we can see in the image below. A destroy operator destroys part of the current solution, while a repair operator rebuilds the destroyed part, of the solution. Usually, the destroy method contains some kind of randomness, such that different parts of the current solution are modified to enable the exploration of the solution search space and get to better solutions. So in this slide, we can see an example of the destroy operator in red and the repair operator in green. So, well, in this slide, we can see the full pipeline for the LOGISTAR project, which is mainly based on 3 steps. So the first step is the processing of the data. Then we have the searching for solutions step, which consists of solving the vehicle routing problem with all its characteristics. And then the last step is to select the best solution that will be the one with the best key performance indicators, which can be ones such as transportation cost, CO2 emissions, filling rates, or empty traveling, or a combination between all these KPIs. So we then have that LOGISTAR is trying to solve a highly non-trivial problem, which is very complex. And for that, LOGISTAR is sustained by a complex architecture, as you can see in this figure, which is implemented by different work packages consisting of different modules and different artifacts. These software artifacts are deployed in Docker containers that communicate or interface with each other, making use of a common message bus, which is available for all LOGISTAR containers. If we zoom into the box, into the LOGISTAR optimization engine, which was using large neighborhood search to explore the state space of solutions in order to try to search for the best solutions. In this slide, we can see the flowchart or the schematics that large neighborhood search follows. So in a first step, it starts with an initial feasible solution, and it keeps on choosing and destroying parts of this solution in order to repair it and try to reconstruct it in better matters. So we try to improve the solution which has been destroyed. If this solution is actually better, we accept it and we keep on with this iterative process in order to try to optimize, to find a better solution until some termination criteria is met. So the implementation of this optimization engine has been coded in Java using JSpeed framework, which is accessible in that link. And JSpeed is a lightweight and flexible tool capable of dealing with wide range of variations of vehicle routing problems, and is also flexible in the sense that allows us to modify, for instance, the cost functions or modify the restrictions so that we can incorporate new restrictions as necessary. So here we can see the algorithm flowchart. So basically, it consists of the repetitions of destroy and repair operators, as previously described, until some termination criteria is met, and the framework gives us access to try to modify the ruining process and the recreation process. So we can incorporate our own restrictions for our own experimentation. In the case of LOGISTAR project, it was necessary to incorporate some adaptations in the computation of solutions to favor conjoint routing and cooperation between companies, which affect the settings of the parameters such as the travel cost, the distance covered by trucks, the service time, transportation time, waiting time. Well, for the evaluation of the project, we have been working in 2 living labs up to now. Even we have a third one defined. So the first living lab is based on backhauling and co-loading. So we are trying to process various information coming from different companies, and we are trying to make joint or collaborative optimization plannings. A second living lab is based on synchromodality, in which the objective is to perform the optimization, the joint optimization of road transportation, rail transportation, and maritime transportation, taking into account that disruptive events can actually occur, which may alter up to a certain extent the initial planning provided by LOGISTAR. And so LOGISTAR needs to be able to adapt to these disruptions and provide a new plan in real time. So we are able to provide a replanning of the previously given solution. Here we can see some preliminary results for Living Lab 1 provided by LOGISTAR, in which we can see the operational planning for some goods that need to be delivered. So in this example, in the upper side, we can see operational planning for the first company, which has been anonymized for this presentation. And in the bottom part, we can see an operational planning for the second company. So we can observe how the system's outputs the track departure times, coordinates for depots, which, as I said, are anonymized for this presentation. Then the tool also shows the action that needs to be performed by the driver, which can be either one of drive, pick up, or deliver. In the right side of the results, the tool shows the pallet number, capacities, time windows, which have also been anonymized for this presentation, alongside the indicators, the most important indicators or key performance indicators, such as the distance covered, the empty running, filling rate, and service time, so we can validate the results with the stakeholders involved. If we do the exercise of analyzing the details of this operational plan, for instance, for company 1, we get that LOGISTAR registers these orders for the driver. So the first action is to drive from some initial depot into some location. This is going to take some time, some kilometers. Then at that exact depot, the driver should perform 2 actions, which are picking some kind of pallet identified by this order ID, and also pick up a second order identified with this ID. So the time windows or restrictions for these pickups should be detailed in the right side. We can now see them because they are anonymized. Then, after making these pickups, the driver should make another action, which is to drive to the next point to make the delivery. So once we reach to that location, the driver needs to deliver the orders with these IDs. So finally, below these actions to be performed, LOGISTAR displays some KPIs for the journey. So we can see the total distance is of 126 kilometers, the empty running has been of 64 kilometers, so the filling rate is 28.8%, and so on. So the full service time it's been of 5 hours and 29 minutes. So this is the information displayed by the LOGISTAR system. If you do the exercise of going into the details of the second operational plan for some other company, so we have that in contrast to the first operational plan where the first step was to drive, now we start at a depot where we are going to do several pickups right there. So we're not driving, we're going to do some pickups there. After doing all of these pickups, we are going to drive to some other place, to some other depot identified with that ID. And at that location, the driver is going to deliver all of those orders. So in this case, the system also displays the journey information, which in this case is consists of a total distance of 314 kilometers, the empty running is of 157 kilometers, and the filling rate is that of 6.7%. And the total service time, it's been of 9 hours and 54 minutes. So all in all, the LOGISTAR project deals with the effective planning and optimization of complex transport operations, taking advantage of horizontal collaboration and cooperation between companies. For the same, it delivers a real-time decision-making tool and a real-time visualization tool of freight transport, which will be based, among others, in global routing optimization engine. It is also one of the objectives of LOGISTAR to increase the load factors of freight vehicles by optimization techniques. And for this, LOGISTAR models several KPIs which are optimized in the process. Finally, here we can see the project consortium members. And well, this is all from my side. So if there is any question, do not hesitate to contact me in the provided email address. And I also invite you to visit the official website of the project for more relevant information regarding LOGISTAR and follow it on LinkedIn and Twitter.